Welcome to E&E. Today, we explore quantum physics. Quantum physics is the branch of science that explains how the smallest particles in the universe behave. At this microscopic level where we study electrons, protons, neutrons, atoms, and photons, nature does not follow the normal rules of classical physics. Instead, particles behave in strange and surprising ways. One of the key ideas in quantum physics is wave-particle duality, which means particles can behave both like solid particles and like waves. Light, for example, can spread like a wave but also hit a surface, like a particle. Another important concept is Heisenberg's uncertainty principle, which states that we cannot know both the exact position and exact speed of a particle at the same time. This is because particles at the quantum level exist as probability clouds, not fixed points. Quantum physics also introduces superposition, where a particle can exist in multiple states at the same time until we measure it. Similarly, quantum entanglement shows that two particles can become connected in such a way that changing one instantly affects the other, even if they are very far apart. These phenomena may seem strange, but they are real and have been proven through experiments. Quantum physics is not just theoretical, it is the foundation of many modern technologies, including lasers, semiconductors, LED lights, MRI machines, atomic clocks, and even the development of quantum computers. Overall, quantum physics reveals a hidden world where reality behaves in ways that challenge our intuition and deepen our understanding of the universe. Quantum physics is a fundamental branch of science that studies the behavior of matter and energy at the smallest possible scales, typically the scale of atoms and subatomic particles. At this microscopic level, the laws of classical physics, which describe everyday objects, no longer apply. Instead, particles behave in ways that seem mysterious, illogical, and sometimes impossible from our normal perspective. For example, quantum particles, such as electrons and photons, do not exist in a single, definite position. Instead, they exist as probability waves, meaning they have multiple possible positions at the same time until they are observed. This idea is closely connected to wave-particle duality, which shows that particles can behave as both particles and waves depending on how they are measured. One of the most famous demonstrations of this behavior is the double-slit experiment, which revealed that electrons can create interference patterns like waves even when fired one at a time. Another central concept in quantum physics is Heisenberg's uncertainty principle, which states that it is impossible to know both the exact position and the exact momentum of a particle simultaneously. This is not due to limitations in technology, but is a fundamental property of nature. In addition, quantum physics introduces the concept of superposition, where particles can remain in multiple states at once. For example, an electron can spin up and spin down at the same time, or be located in two places simultaneously. When a measurement is made, the particle's multiple possibilities collapse into a single outcome. This principle forms the basis of quantum computing, where quantum qubits can store multiple states, making calculations extremely powerful. One of the most puzzling phenomena in quantum physics is quantum entanglement. When two particles become entangled, their properties become linked, regardless of the distance between them. If the state of one particle changes, the other reacts instantly, even if they are separated by thousands of kilometers. Einstein famously called this spooky action at a distance, but modern experiments have repeatedly confirmed that entanglement is real. Another important concept is quantum tunneling, where particles can pass through barriers that would be impossible in classical physics. This occurs because quantum particles behave like waves and have a probability of appearing on the other side of a barrier. Quantum tunneling is essential in technologies like scanning tunneling microscopes and plays a role in the nuclear fusion reactions that power the sun. Quantum physics may seem strange and counterintuitive, but it is one of the most successful and accurate theories ever developed. It has led to countless technological advancements that shape our modern world, including lasers, semiconductors, transistors, solar cells, MRI machines, LED lights, GPS systems, and atomic clocks. Today, quantum physics is driving new revolutions in technology through fields like quantum computing, quantum encryption, and quantum communication. These technologies have the potential to transform computing, medicine, cybersecurity, and many more areas. Overall, quantum physics reveals a universe that is far more complex, interconnected, and mysterious than we can observe, with our eyes showing that reality at the smallest scales behaves in ways that stretch our imagination and deepen our understanding of how the universe truly works. Quantum physics is extremely important in modern physics because it forms the foundation of our understanding of the microscopic world and explains phenomena that classical physics cannot describe. It provides the theoretical basis for understanding the behavior of atoms, electrons, photons, and all fundamental particles. Without quantum physics, we would not be able to explain how atoms bond, how light interacts with matter, or how energy levels work inside atoms. Modern physics depends heavily on quantum principles for developing advanced technologies such as semiconductors, lasers, transistors, and MRI machines devices that power the modern digital and medical world. Quantum physics also plays a crucial role in explaining nuclear reactions, chemical reactions, and the structure of materials. It has given rise to entirely new fields like quantum computing, quantum communication, and quantum cryptography, which are expected to revolutionize future technology. In summary, quantum physics is essential because it not only explains the fundamental nature of reality but also enables the technological advancements that define the modern era. The relationship between quantum physics and electrical engineering is profound and deeply connected, as almost all modern electrical devices operate on quantum principles. Electrical engineering is the field that deals with circuits, semiconductors, communication systems, power electronics, and digital technology, all of which fundamentally depend on the quantum behavior of electrons. Quantum physics provides the essential framework for explaining how electrons move inside materials, how energy levels function within atoms, and how electric current flows at the microscopic level. The very heart of modern electronics, semiconductors, work because electrons can jump between distinct quantum energy bands. Critical components like transistors, diodes, light-emitting diodes, or LEDs, lasers, solar cells, and integrated circuits are all designed and optimized based on quantum mechanical models. Furthermore, advanced communication systems, such as fiber optics, rely on the quantum behavior of photons to transmit information. Even highly precise electrical measurements, advanced sensors, and breakthrough materials like superconductors are understood and developed through the lens of quantum principles. In essence, without the discoveries of quantum physics, the field of modern electrical engineering as we know it today would simply not exist. The benefits of quantum physics in electrical engineering are vast and transformative. First and foremost, it serves as the foundation of semiconductor technology. Quantum physics explains the concepts of energy band theory, the movement of electrons, and doping processes, which are all critical for creating the diode, transistors, integrated circuits, and microprocessors that power our digital world. This leads directly to the development of modern electronics. Devices like LEDs, lasers, photovoltaic cells, and optical sensors all operate by harnessing the quantum transitions of electrons and photons between energy states. Moreover, quantum principles have enabled the creation of high-speed and efficient devices. By understanding quantum behavior, engineers can design electronic components that are smaller, faster, and more energy, which are now ubiquitous in our computers, smartphones, and communication devices. This also leads to significant advancements in communication systems. Quantum mechanics is the science behind fiber optic communication, photonics, and emerging technologies like quantum encryption, which promises to ensure highly secure and high-speed data transfer for the future. The rise of quantum computing represents another major benefit for electrical engineers. These revolutionary machines promise unprecedented processing power for complex tasks such as simulation, artificial intelligence, cryptography, and big data analysis. Finally, quantum physics provides a better understanding of materials. The study of superconductors, nanomaterials, and advanced sensors relies heavily on quantum principles, allowing engineers to design and build high-performance electrical systems with previously unimaginable capabilities. Despite its incredible benefits, quantum physics also presents several demerits and limitations within the field of electrical engineering. One of the most significant hurdles is its reliance on highly complex mathematical concepts. Quantum physics is notoriously difficult to understand and requires a deep knowledge of advanced mathematics, which can make the design and modeling of quantum-based devices exceptionally challenging for engineers. Another major limitation is the expense of the technology. Quantum devices, such as quantum computers and systems involving superconductors, often require extreme operating conditions, such as extremely low temperatures and precise environmental control. These requirements dramatically increase the manufacturing and operational costs, making them inaccessible for many applications. Furthermore, it is incredibly difficult to apply quantum effects in a practical, everyday setting. Quantum phenomena are extremely small and highly sensitive to external disturbances or noise. Maintaining stable quantum states, a requirement for many engineering applications, is a monumental technical challenge. The current use of these technologies is also limited. Many advanced quantum-based technologies, most notably quantum computing, are still in the experimental or early developmental stage. They are not yet widely available for everyday engineering tasks, confining their use to specialized research institutions and large corporations. Lastly, quantum research and development require highly specialized equipment. This includes high-precision measurement instruments, ultra-high vacuum chambers, complex laser systems, and cryogenic cooling apparatus. Most university and commercial electrical engineering labs cannot afford this level of sophisticated infrastructure, slowing down the pace of innovation and practical application.